Hey guys, welcome to recitation 15.1. In this recitation, we will, like I said last time, we will be talking about integral inequalities from my worksheet. In fact, I'll solve 4 problems involving integral inequalities. Some of them were given at previous Putnam exam, some others at other contests, and so on. All right, so let's get started. Let me start with a problem, the fairly easy problem, which was given in the Putnam competition back in 2014, I think. So the problem has the following statement. So let's say problem 1. So this was a Putnam B2 in 2014. The problem has the following statement. So suppose that that a function f, right? That f, sorry, is a function on the interval closed 1, 3, such that -1 is less than f of x is less than 1 for all x. And we have this condition here that the integral of f is 0 on the interval 1, 3. So the question is, how large can this integral from 1 to 3, but this time of f of x over x dx can be? That is the question. Well, this is pretty easy because as you can see, the function is defined on 1, 3, but it's between -1 and 1. So we can do something about the integral. And in fact, we can manipulate this integral. Maybe we can manipulate this integral in terms of this one here. So maybe we should do that somehow. All right. So let's see. So what should we do? So let's look at this integral, right? So let's define. So let us define the function f of x to be the integral from 1 to x of f of t dt. And t is between in the interval 1 and 1, 3, right? Sorry, x. All right, so we have this. All right, so what do we know about this function? Well, if you look at it, f of 1 is 0 and f of 3 is 0. So clearly, f of 1 is 0, and f of 3 is 0. All right, great. And moreover, we can make the following crucial observation, that f of x is less or equal than the minimum between x minus 1 and 3 minus x. And this will be a crucial observation because I would like to use this, right? Well, that's pretty much clear. All right, so now what we can do is we would like to express this integral that we want to maximize. So we have that the integral, let's write it from 1 to 3 of f of x dx, f of x over x dx. And we would like to integrate by parts. So, so here integrating by parts. Integration by parts. Because we can write this as the integral of so this is f prime of x over x dx. So this would be f of x over x from 1 to 3 minus the integral from 1 to 3 of f of x over x squared, right? Dx. Well, here we don't have any problems. This would give us 0, right? Right. Here we have plus. So this would be equal to the integral from 1 to 3 of f of x over x squared dx. All right, great. But let's use this observation here. So we would like to use this. And now what we're going to do is we're going to break the integral into two parts. So this would be the integral from 1 to 2 of f of x over x squared dx plus the integral from 2 to 3 of f of x over x squared dx. All right, and now let's see. You see, this will be less or equal. Let's see, put it here. So the first part, f of x will be less or equal than x minus 1 on the interval 1, 2. And the second integral from 2 to 3 will be 3 minus x over x squared dx. All right, and now the only thing we need to do is just to compute these integrals. So let's see, well, this is just, if you want to do it. So this would be the integral from 1 to 2. Okay, let's do it. Plus what you can see here, we have some natural log. And in the end, if you do the computations here, so I'll leave this to you as an exercise. So computations. So exercise for you. This will give us log. So here I have 4 over 3. I hope I didn't computations correct. So that would be the, this is how large can this integral be. That's it. That's the problem. It was fairly easy. So once you made these observations and once you define this function, that's pretty easy. So that was a Putnam B2 in 2014. Yeah. All right. The second function that I want, the second problem that I want to do is another Putnam problem. So let's see problem 2. But this is an older Putnam problem. It's now I saw it as a preliminary exam problem in many universities now. But anyway, so this was a Putnam B4 in 1973. The problem has the following statement. So let f be a function having continuous derivative 0, 1, and with the property that the derivative is between 0 and 1. Also, we suppose that f of 0 is 0. So prove that we have the following inequality. That the integral from 0 to 1 of f of x dx squared, everything squared, is greater or equal than the integral from 0 to 1 of f cubed of x dx. And also, we would like to give an example in which equality occurs. All right. So this was a Putnam before 1973. So, well, as you can see here, we have a function with a continuous derivative. So in other words, anyway, we have a C1 function. But we have this condition here. If you look at it, we have this guy here, right? So we know that well, we have a condition about the derivative being between 0 and 1. We also have this condition that f of 0 is 0, right? And well, we're trying to prove an inequality if you look at it. But if you think of something like Cauchy-Schwarz or Holder or whatever, forget about it. Well, there is no way to do that because Holder or Cauchy-Schwarz will give us a lower bound and we need an upper bound. So there is no way we can apply Cauchy-Schwarz here. But instead, since we have this, since my function is a C1 function, right, it has a continuous derivative, then I don't have any problems. I can differentiate once I put my hands on the right function. So first, let's break this into pieces. Well, you can actually do it directly, but I'm trying to over-explain it a bit, although it's pretty simple. So let me consider this function. So define, I'm going to define a kind of a combination between integrals and between the integral of f and f, and take the derivative. Maybe I can see if some functions are increasing or not, and then I can play around with that. But first, let me define the function. And the function I'm defining is the following. So g of t, let's say. This would be 2 times the integral from 0 to t of f of x dx minus f of t squared. And t is between 0 and 1. All right. If you look at this function, right, see, just the difference between the integral minus the square of f. Well, clearly, g of 0 is 0. That's obvious, right? Because f of 0 is 0 as well. All right. And if we take the derivative, and of course, the function is differentiable. Since f is c1, the integral is differentiable, so I don't have any problems. I hope that's obvious to you. And the derivative, g prime of t, this would be 2 f of t, right? Minus 2 f of t, f prime of t. Okay, great. So we can just factor here. So this would be equal to 2 f of t times 1 minus f prime of t. Beautiful. So this means that since this is greater or equal than 0, then this is greater or equal than 0. So G is increasing, it's non-decreasing. And this implies that G of t is greater or equal than G of 0, which is 0. So G of t is non-negative, right? So f of t times G of t, capital G of t, is non-negative for all t in 0, 1. All right, so what? So far we have this function, but now let me define this function. So what I'm going to do is I'm just going to look at, you see my conclusion, I have to prove this inequality. So instead of 1, I'm just going to take a variable t, and I'm going to consider the difference between the two. I'm going to differentiate with respect to t, and then we'll evaluate, we'll see what happens with that function, if it's increasing or not, and then we'll evaluate for t equals 1. So that's basically the main idea of the problem. So let's do this. So now now we define a function let's say f of t, capital F of t, as the integral from 0 to t of f of x dx squared, right? Minus the integral from 0 to t of f cubed of x dx, or t in 0, 1. Okay, so we have this. Okay, so just like I said, we're going to differentiate this, and we would like to see what happens. All right, let's do that. First, let's make an observation. Again, f of 0 is 0. That's obvious. And the derivative, right, with respect to t, right, f prime of t is is what? Is 2 times the integral from 0 to t of f of x dx times f of t minus f cubed of t dt. If we factor here, this would be nothing else than just okay. So we can write this as f of t times g of t, right? So where g is the function that we defined in the first place. You see this function here. So that's g of t. All right, great. What do we know about that function? We know that it's, well, we actually proved here, right? So we have that this guy here is non-negative. The whole thing is non-negative for all t is 0, 1. Great. So this means that f is non-decreasing. And this means that f of t is greater or equal than f of 0, which again is 0. So there we go. So f of t so in particular, f of 1 is greater or equal than 0, which is our conclusion, which is exactly what we wanted to prove. right, great. Well, and now we're asked about the equality case, right? So we would like to see when equality holds true. So the equality case holds true if, let's see, when did we, so basically it holds true if f of t times g of t, capital G of t, right? This guy is the same as f prime of t. And also when both of these are 0 for all t and 0, 1. All right, great. Well, you can solve this. This implies you have only two options. So I'll leave this to you as an exercise. Either f of t is 0 or f of t is t. So these are the only two functions that verify. Anyway, so that's the problem number 2 from this seminar. Right? It's fairly easy as well. All right, so I have 2 more problems in mind. And the next problem will be problem 3 in lecture 15.2, I think. Yeah, so 15.2, when I talked about integral inequalities, I've talked about this problem, but now I'm going to extend it a bit. So the problem has the following statement. So let be an integrable function such that we have the following condition. The integral of f is the same as the integral of x of f. And this is the same as the integral of x squared times f. And moreover, all 3 of these are 1. And then guess what? The integral from 0 to 1 of f squared is greater or equal than 9. Well, in the lecture, if I remember correctly, we did I didn't have degree 2 here. I have only the integral of f is the same as the integral of x of f, x times f. Both of them are equal to 1, and then show that the integral, the 2 norm, let's say, of f is greater or equal than 4. Now, if I add up the quadratic term, and if I make it 1 as well, then instead of 4, I have 9. And probably I could generalize this. But anyway, we're not going there. So let's see this one. Well, pretty much this has the same idea. Well, in fact, I'll show you 2 solutions. One of them will be in the same spirit. Well, in fact, both of them will be in the same spirit as the other problem that I discussed in the lecture. So let's see solution 1. So as you can see, I have this condition here. And if I apply, again, I'll leave this to you as an exercise. If you take just to apply the Cauchy-Schwarz to each one of them, you're not going to go anywhere. For example, let me just try naive way. So by the Cauchy-Schwarz, let's say, let me just apply this in a very naive way. What do we have? So we have, let's say, this one here, f squared times, let's say, the integral of x squared is greater or equal than the integral, let's say, of x squared of x times f of x dx squared. This guy is 1. And now this guy is just, it's integral of x to the 4th, so it's 1/5. So this implies that the integral from 0 to 1 of f squared dx is greater or equal than 5, which is not good enough. Well, you can try with the others, and you'll get 1, or also you'll get x will be 1/3. Again, not good enough. So we kind of have to find a polynomial, let's say, right? That will be the best guess that the best function that we could look for. So we were looking for a polynomial. So the best thing that could approximate my function f. So we're looking for a quadratic polynomial. Let's say p of x is ax squared plus bx plus c, right? Such that these 3 conditions are met. So such that we have these 3. Let me write them there. The integral from 0 to 1 of p is 1. The integral from 0 to 1 of x times p of x dx is 1. And the integral from 0 to 1 of x squared p of x dx is 1. Well, you can plug it in, right? You'll form a system of 3 equations, 3 unknowns, and you will solve this. So you will have a system of 3 equations, 3 linear equations in A, B, and C. Right, so you just plug it in, you compute those 3 integrals, you'll have some crazy, well, I wouldn't say that crazy, but it's a system of 3 linear equations. You're in A, B, C, and once you solve this, and by solving this system, you can solve it by using the traditional methods like in linear algebra, like elimination, Gauss elimination, and so on. You can solve using Cramer's rule. Anyway, I'll leave this to you as an exercise. It's pretty much linear algebra super standard problem, like a linear algebra exam problem. So by solving this, we'll find that A is 30, B is, what was it, negative 24. I solved this. Let me find it. And C was 3. Okay, I hope, yes. So the polynomial P of x is 30x squared minus 24x plus 3. So this is the optimal polynomial, the optimal quadratic polynomial that we're looking for, that verify these 3 conditions here in the system. All right, that's great. So what we can do now is just applying, doing the typical stuff. So we're gonna consider this integral. This is clearly non-negative. And now we're just going to do the computations here. So this would be the integral of x squared minus 2 times the integral of p of x times f of x dx plus the integral from 0 to 1 of p squared of x dx. All right, so let's do the computations here. So this would be equal to the integral of f squared of x dx minus 2 times, this is 30x squared minus 24x plus 3 times f of x dx plus this integral 30x squared minus 24x plus 3 dx. All right. So this would be the integral of f squared minus, and now let's do some computations. Oh my God, I hate it, but anyway, sometimes we have to do this. 30 times square root of f of x dx minus 24 times this integral. That's 3 times the integral of f plus, and here is a square, plus, let's be careful with this one here. So I have a 3, I can factor a 3, which is a 9. And this is 10x squared minus 8x plus 1 squared dx. All right, great. Let's see, this will give us minus 2 times. And now let's see, this is 30 minus 24 plus 3 plus 9 times this integral. Okay, which will finally give us the 24, 6 plus 9 minus 18 plus 9 times, and this integral you can actually compute it. And I'll leave this to you as an exercise because I don't want to do too many computations. This is 1. Right? So this would be the integral of f squared minus 9. So the conclusion follows immediately. All right, so that's the first solution. Now let me give you another one. So solution number 2. This will be very tricky. In fact, let me say it, very tricky. It's not as conceptual as this one, where actually we're looking for. So I'm going to do the following trick. So I'm going to do in the same fashion as I did the problem from the lecture. So bear with me. So we have the following. Look here. 9 is 3 squared. But 3 is nothing less than 10 minus 8 plus 1. Everything squared. All right, great. But actually, this is 10 times 1 minus 8 times 1 plus 1 times 1. Everything squared. And now, this one will be replaced by the first integral of x squared times f, the second one by the integral of x times f, and the third one by the integral of f. So let's do that. So this would be 10 times the integral of x squared of f times f plus the integral of f squared. And this would be, if we factor everything here, this is nothing else than just the integral of 10x squared minus 8x plus 1 and the of x dx. Everything squared. Great. Now by the Cauchy, this is less, and this is, guys, less or equal by applying Cauchy-Schwarz inequality. By what? It's less or equal than the integral of 10x squared minus 8x plus 1 squared times the integral of f squared of x dx. This guy is 1, and there you go. So finally, this implies that the integral of f squared of x dx is greater or equal than 9. And we're done. Of course, the equality case is pretty much clear when it holds, but I'll leave this to you. All right, so this was problem 33 in my list, and I have one more to go. Where is it? Anyway, problem 4, which says the following. It's pretty similar. So let me consider f to be, all right, I'm going to write it like this. F is a C1 function on 0, 1, real valued. Such that we have something very similar, such that the integral of f is the same as the integral of x times f. And it's 1. I would like to show that the integral, the derivative squared is greater or equal than 30. Well, as you can see now, at this point, I have f is a C1 function, so it's a differentiable function, and its first derivative is a continuous function. All right, that's great. So maybe I can do some integration by parts. Right, so this is, let's not forget, this is an important piece of information, and of course I have this, which I can do something about it. So I can integrate by parts, which that's great. So let's integrate by parts. So integrating by parts, we have, let's see, what do we have? So let's look at the first integral. So this is 1 x prime times f, which is f minus the integral from 0 to 1 of x times f prime of x. And this guy is, so 1, it's f of 1 minus the integral from 0 to 1 of x f prime of x dx, right? All right, right. Now let's look at the second one, right? So x times f of x. So maybe this is x squared over 2 prime times f of x dx. So this is 0 to 1 minus this guy here. So again, I'll have 1/2 f of 1 minus 1/2 the integral from 0 to 1 of x squared f prime of x. All right. Okay. But let me rewrite this a bit. So rewrite this. If we rewrite the two equalities above, we have, so let's see. See, the first is, oops, sorry about that. So the first one is 1 equals f of 1 minus the integral from 0 to 1 of x f prime of x dx. And the second one is 2 is f of 1 minus the integral from 0 to 1 of x squared times f prime of x dx. All right, so let's call this star and this double star. I have these two relations, so maybe I should do something about it. Keep in mind that at some point I need to well, I have in mind to apply Cauchy-Schwarz inequality, right? Because I need to prove an inequality about the 2 norm of the derivative. So the best indicator to do that would be to apply Cauchy-Schwarz. Okay. So what if we subtract 1 from 2? So this implies that 1 equals let's see if this works. All right, so this would be equal to the integral of f prime of x. All right, great. Great. Okay, now let's apply by the Cauchy-Schwarz inequality. Obtain that 1, which is this guy here, is less or equal than the integral of x times 1 minus x squared dx times the integral of f prime of x squared dx. All right, and now the only thing we need to do is just to compute this guy here. Well, I'll leave this to you. This guy as an exercise is just 1/30. I don't want to do this computation, but you can believe me. So once I have this computation, so therefore this implies that the integral of f prime of x squared dx is greater or equal than 30, and we're done. You can also analyze the equality case. In fact, that would be very interesting because the equality case will hold true if the derivative, if f prime of x is some constant lambda times x times 1 minus x. And you can integrate, and then you'll find the 2 constants. Anyway, it's a little bit of a computation, but I'll leave this to you again as an exercise. All right, guys, I think I'm gonna stop here for the recitation. Well, the next recitation, I do have a surprise for you. I will discuss only 1 problem, but you will see plenty of solutions for that problem. It was a Putnam B2 in 2007. Again, it's an integral inequality, but we have to estimate. It's a very sharp estimate, though, and you will see plenty of techniques. You will see even convexity, mean value theorems, Taylor's theorems, and so on. So you can even see Lagrange interpolation polynomial involved there. Anyway, that would be the next recitation. All right. Thank you very much. I'll stop here. Bye-bye.